Hi, in this video we are going to show you a demo of how our project works. We start introducing the architecture of the system to explain briefly how the employed components interact and which kind of services has been involved. All the information and settings related to the user are stored in a main catalog, which is a JSON file made available through a REST web service and reachable with a static address owned by each user in another JSON file. A new user can be added to the catalog with the new user microservice. In the first step, we retrieve the user's data from the IoT cloud, and to avoid redundancy for each user, all the information needed to access the cloud, such as API key, certificate, client ID, client secret, and the access token, are taken from the main catalog with a RESTful style communication. This kind of strategy is used also to retrieve the user's data from the IoT cloud. Then, a publish-to-describe communication based on Mosquito Broker manages the data of interest, making them available for the control strategies microservices. To check the user's health conditions, 4 parameters have been considered, and for each of them a control microservice have been developed. Firstly, is verified to each user the retrieved weight, BMI, water percentage, and muscle mass data belong. Then, we can manage and evaluate them. The obtained results are sent to 3 different applications in order to show them to the user in a more user-friendly way. In particular, in the TeamSpeak user channel are shown the trends of the data related to the 4 different parameters. These graphics can be also displayed in Telegram with a specific command. Anomalous results obtained from the control strategies processing trigger alarms, and Telegram messages are automatically sent to the user to make him aware about his conditions. Finally, to show to the user his global status, all the information collected in Telegram and TeamSpeak are grouped in his personal Freeboard page. All the mentioned actors will be presented in detail in the next sections.
All the settings and information related to the users are stored in a catalog shared among them through a web service, which makes it available online. Each user owns a JSON file containing the address of the class that manages the catalog. The JSON file containing the catalog is located in a server reachable through a static address. The class managing the catalog allows both reading and editing. In this way, the inconsistency is avoided because there are no catalog copies. The only existing version is the one stored in the mentioned server. In this file, we can also see another class devoted to keep update the dashboard sources file, available at another online service and reachable in the same way of the catalog. Until the script is running, the catalog will be reachable at this address, and every time a user will ask for the file, the request will be checked in the shell. The main catalog has a hierarchical structure. Each external key groups a list of dictionaries of the same type. For instance, at the user's key, we can find a list for each user whose identity can be matched with the ID key. Moreover, also the information to access to the personal IoT cloud, to the third-party services like Telegram and TeamSpeak, the threshold used by the control strategies, and the list of devices associated to the user are collected here. A last external key corresponds to the broker address.
A new user can be added to the catalog through a specific microservice developed in RESTful style. The user will enter the data from the Raspberry shell, filling only the required field. There will be some remaining fields, like those related to technical information of eye health, that will be automatically filled. The changes made will be saved updating the catalog. Let's see how it works. As we can see, the added data appear in the catalog. Moreover, the updating request is recorded in the shell.
The first step is to retrieve the user's data from their iHealth cloud. For this purpose, the personal user's access information are taken from the main catalog, and for each user, the data are retrieved from the cloud with a RESTful style approach. In order to have a more reliable evaluation of the health conditions, only the more recent data are processed. Thus, only the two last measurements, being at least 1 day away, are taken into account. At the beginning, a client is created and connected to the broker. Then, for each user, the processed data are published, and if no new data are available, nothing will be published and the notification will appear on the shell. The new data will instead be published for each parameter in a JSON messages composed by the user ID, the two last values, the period of time in day elapsing between them, the date of the last acquired measure, and this same in UTS. Each message is published with a specific topic. Now data are available and the broker can send them to the subscribers with an asynchronous communication. For each user are made subscriptions for the different topics. When a message is received, a message notifier reporting also the topic will appear on the shell. Since the order of the incoming messages is not exactly predictable, a screening of the messages received is carried on by checking the user's ID. To process and evaluate the data according to the topic, a specific microservice is called. For instance, if a message with the weight topic is received, the weight control strategy is called. The analysis results involve the updating of the ThinkSpeak users channel, the sendings of alarms, if needed, to the user to the Telegram bot.
The last values acquired for each parameter are retrieved from the messages received by the subscribers and passed to a specific MEDOT in order to update the user's ThinkSpeak channel. Thus, the trends of each parameter are updated. The same graphics are automatically shared and displayed in Freeboard. Moreover, since weight trend is the most meaningful, user can ask for it also through the Telegram bot.
Through Telegram, we developed two different kinds of services to support the user. One aims to make him aware about his health condition by sending him alarm messages automatically. The other one provides data on demand. For this purpose, we created the GIM bot, which works thanks to a Python script file. Every time a user connects to GIM bot asking him data, his Telegram ID is retrieved from the chat, allowing the identification of the user in the main catalog and his ThinkSpeak channel ID. 5 different commands have been implemented. In particular, 4 of them are devoted to manage the different parameters, and the remaining one provides to the user the ThinkSpeak link of his weight trend. Let's see how GIM works.
To better understand how the control strategies work, now we test the different microservices with fake data for each parameter. For this purpose, we created 4 different JSON files having the same structure of the real messages published. Each of them is associated to a specific topic, so to a specific microservice. Now we consider only one of the microservices implemented, since the structure among them changes only for the kind of the topic and the related data analyzed. Also, a specific catalog having the same structure of the one previously described has been created. The control strategy aims to evaluate the changes between the 2 values provided in the message received. First of all is evaluated the time. The evaluation is based on the period of time elapsing between the last acquisition date in UTS and the current one. If the difference overcomes a fixed threshold, an alarm is triggered and a message inviting the user to record new data is sent to him through Telegram. This is to avoid evaluating data not reliable because considered too much old. Instead, if the data are recent, the difference between the 2 last measurements is computed. If the results overcome the weight threshold, an alarm is triggered and a message is sent through Telegram to the user to make him aware of his actual health conditions.
In order to better show to the user his current conditions and the global trends of each kind of data acquired, we develop a more user-friendly interface through Freeboard. Firstly, we load a previously saved configuration file. The page opened is related to a specific user whose data are taken from 2 source files available thanks to a static URL. In the first one are stored the data related to the last measurement, and in the second one are stored the threshold from the main catalog. On the top of the page are shown the user personal data, such as name, surname, the user ID, and in addition, the date of the last acquisition. The following sections present the information of the 4 different acquired parameters: weight, BMI, muscle, and the water value. On the right of the screen are reported the trends taken and synchronized with the TeamSpeak user channel. And on the left, there are some gauge indicating the current value of each parameter. The gauge values are compared with the user's thresholds, and in order to have an effective visualization of his actual health conditions, we inserted below some light indicators. A green light is for good conditions, a yellow one is for borderline status, and a red light is for critical weakness. As we can see, the light indicator switches instantaneously if the value changes overcoming the threshold.